just like spend 30 seconds reminding you what we did yesterday. I think I did like a 6 out of 10 job of writing out the definition. So here's the main definition again, the definition of a triangular basis. It's a silly axiomatic definition. The point is it's just useful in lots of practical situations where you can find such a basis for your algebra. It gives you a very quick way of establishing lots of strong homological properties for the algebra. If you remember, we defined standard modules, and we got a classification of the irreducible modules as the simple heads of the standard modules. And I didn't mention any of the homological properties, but you get lots of properties that maybe you're familiar with if you've worked with highest weight categories in Lie theory or something like that. I guess I could have said that any quasi-hereditary algebra has a triangular basis of this sort, but actually a very special triangular basis of this sort, where the diagonal, remember my basis was x, h, y, and the diagonal part was the h part. The ones coming from quasi-hereditary algebras, you really don't need the h part, it really plays no role. So that was what we did most of the time yesterday, and then I ended up in the last few minutes with this classical example, and I kind of gave myself 2 out of 10 for this because I didn't really have enough time to do it justice. But this classical example, this Q-Schur category, the path algebra of the Q-Schur category has this very classical triangular basis of codeterminants constructed by Green. And that is exactly one of those situations where this is actually quasi-hereditary, so the H part of my triangular basis played no role in this example. So today I'm going to do a new example, which is really what this theory is there for, and the H part is going to play a big role, and that's the whole deal. So let's see where we actually are. So the good news is that second part of yesterday's talk, that example, the Q-Schur category, it doesn't matter that I did a 2 out of 10 job because I'm not going to use that at all. But I am going to assume that this definition of triangular basis, my 6 out of 10 job, that you vaguely remember some of the words. So the thing that's going to be different today is I'm going to work in a graded setting. So I'm going to add gradings to everything. So if you like, I'm enriching in graded vector spaces. Remember, I'm always working over a field. But so maybe let's just write down just a few conventions. If I have a graded vector space, so everything is Z graded. So V sub D is the degree D piece of my graded vector space. I just wanted to write down my conventions because everyone makes a different choice, it seems. So if you have 2 graded vector spaces, then the space of linear maps from V to W, this is again graded. And so this is what I write. I put a subscript D there, the degree D linear maps from V to W. They take the degree I part of V into the degree I plus D part of W. I think that's a pretty standard convention. I write Q for the downward grading shift functor on graded vector spaces. So if you have a graded vector space V, QV, I've shifted the grading down, so its degree D piece is, I think I might have got that right. So that's my convention for Q. Let me see, what else do I want to say here? I will write dim Q of V for graded dimension. So the Q, of course, I mean, we're categorifying quantum groups. So I want this Q there. It's the Q in your ground field for your quantum group. That's always coming from the grading on when I'm categorifying. So that's the point of grading. I'll write dim Q for the graded dimension of V. So that's just the dimensions of the graded pieces. Q to the minus D, that's the right convention if Q is downward grading shift here. This, of course, only makes sense if V is graded finite dimensional, which means that all of these graded pieces are themselves finite dimensional. So I'll use that phrase, graded finite dimensional, a lot. And then this makes sense as some sort of formal series. Probably I want V to be bounded below so that the VDs are 0 for sufficiently negative D, and then this will actually be a formal Laurent series, I guess, in Q inverse with this connection. So let me see, is that everything I want? Then, for example, V as a graded vector space, I mean, there's only one irreducible K module in this graded category, which is K itself. And when I write K and think of it as a graded vector space, it's always in degree 0. So that's the only simple graded vector space up to isomorphism and degree shift. And then a general graded vector space, that's just the one-dimensional one in degree 0, and I just write direct sum dim Q of V. So of course this is a formal series, but when I put a formal series in the exponent, direct sum Q means grading shift QV. Direct sum Q squared plus 5Q means Q squared V direct sum QV 5 times. So I take direct sums to these sorts of formal series, and it's exactly set up so that's just my grading conventions. Is it clear enough? I guess later on we're going to actually be doing graded algebras. So we're going to be looking at modules over graded algebras, not just vector spaces over the graded algebra K, but over a general graded algebra. And then I will just use the usual notation for like composition multiplicity. If V is a graded module over a graded algebra, and you have some irreducible graded module over that graded algebra, I will use that notation for the graded composition multiplicity. So in the case of F, graded composition multiplicity is exactly this Q dimension. All right, that's everything I'm going to do on the board. So let's start off today with an example of a graded algebra. I just want to have one concrete example of the sort of graded algebra that's relevant for what I'm doing. So the example I'm going to give you is the Nil-Hecker algebra. So this is well-known from Schubert calculus, for example. So there it is, NHN, the Nil-Hecker algebra. It's got generators x1 through xn, which are in degree 2, and tau 1 through tau n minus 1, which are in degree minus 2. I'm not going to write down the relations for the algebra. Instead, I'm going to tell you that it acts on the polynomial algebra. So pol n, I just use that as short for the polynomial algebra in x1 through xn. X's are all in degree 2. And the way the Nil-Hecker algebra acts on the polynomial algebra, the generator xi of the Nil-Hecker algebra just acts by multiplication by xi. And the tau i's, the way these guys act on polynomials, they act by these de Maizière operators, these divided difference operators. I think that's kind of well known for everyone. So de Maizière lowers the degree of a polynomial, so it subtracts 2 from the degree because my x's are in degree 2. In fact, one more little piece of notation. I write sim n for the subalgebra of pol n consisting of symmetric polynomials. Okay, so sim n is symmetric polynomials in n variables. The action of the Nil-Hecker algebra on pol n is actually an action that commutes with any symmetric polynomial. So that means that this action of NHN on pol n, if you look at the algebra homomorphism induced by that action, it gives you a homomorphism from the graded algebra NHN to this graded endomorphism algebra of sim n endomorphisms of pol n. And the absolute basic fact that that everything is rests on in this whole subject of categorification these days is that actually the Nil-Hecker algebra is isomorphic to that endomorphism algebra, n sim n of pol n. And that's important because, well, polynomials, pol n, is a free module over symmetric polynomials. Pol n is a free graded sim n module. So this is what I'm writing here. Pol n is a free graded sim n module. And to get a basis, you take these monomials, x1 to the I1, x2 to the I2, dot, 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 xn to the In, where the powers there 0 is less than or equal to ij is less than or equal to n minus j. So the first power, x1, the power could be from 0 through n minus 1. The second power, x2, the power could be from 0 through n minus 2, and so on. So the number of these monomials in this homogeneous basis for pol n as a free graded sim n module, the number of monomials is n factorial. So it's literally perhaps the most classical fact in algebra that I can think of is that pol n is a free sim n module of rank n factorial. Everything's graded for me, right? So when I count rank, I should count rank as graded rank. So actually the graded rank of it is this remember square brackets was quantum integer. So this is this square brackets n factorial, that's quantum n factorial, and then there's a shift by q to the minus n choose 2 there to make that correct. That's the graded rank. That's just counting the degrees of the basis vectors there, using my conventions about q that I've written. So a consequence of that is that this endomorphism algebra, if pol n is a free sim n module of rank n factorial, that endomorphism algebra is just a matrix algebra. It's just n factorial by n factorial matrices with entries in sim n.
Sorry, I have a silly question about the grading conventions.
Yep.
If for example, if you have one copy of k in degree -1, is the graded rank q to the 1 or q to the -1?
That would be the graded dimension would be q.
But then when you say k direct sum to the dimensions, you say k direct
K direct sum
squared?
q would be qk. That would be k shifted in degree -1 because it's the downward degree shift.
Is that d plus 1 then, or
Then
qv
that's
of d is at d
okay,
plus
so if
1?
I put k in degree 0, so this is in degree -1. So I want the degree -1 part to be. I think I did mess that up, didn't I? It's always good. I have to blame Wei Chung for telling me I needed to switch my convention. So this is downwards. So if v is in degree 0, qv is in degree -1. Did I get it right now? Maybe. Okay. So the consequence of that discussion is that this nil-Hecke algebra then is just a matrix algebra, a graded matrix algebra, n factorial by n factorial matrices with entries in the algebra of symmetric polynomials. And of course, the algebra of symmetric polynomials is very easy. Graded algebra is just itself a polynomial ring, but it's positively graded, it's connected. In degree 0, it's just the field K. So there's one irreducible graded sim n module up to isomorphism and grading shift, namely just the field K, which I always put in degree 0. That's the only irreducible sim n module up to grading shift. And it follows, therefore, that the only irreducible nil-Hecke module, the only irreducible graded NHN module is just column vectors over the irreducible sim n module. So it has just one irreducible as well, up to isomorphism and grading shift, and that's of dimension n factorial. So I denote that irreducible by L sub n of n. That just kind of fits the notation of the general framework we're talking about. And I choose the grading shift on this. This is the irreducible nil-Hecke module graded, so that its graded dimension is quantum n factorial. So that's just me fixing the grading shift in a natural way. And then I write Pn of n for the projective cover of Ln of n. Actually, that is just this polynomial representation of the nil-Hecke algebra, but you have to put in a degree shift into the polynomial representation to match that graded rank, so that I'm shifting it down, and that's the actual projective cover in the category of graded modules. Okay, that's things we need about nil-Hecke algebra. Does it make it fairly clear? Okay, so we've got the nil-Hecke algebra NHN. It's got this special graded irreducible of graded dimension n factorial. That's Ln of n, and the projective cover Pn of n is basically this polynomial representation just shifted in degree, so that the cover map from P to L is degree 0. So this nil-Hecke algebra NHN, I mean, it's a lovely algebra. It's just a matrix algebra, but it's a matrix algebra with entries in symmetric polynomials. So it's of course infinite dimensional, but it's graded finite dimension. The graded pieces are all finite dimension. In fact, the nil-Hecke algebra, it's the grading on it is graded finite dimensional, so that's this degree d piece is finite dimensional for each degree, and it's bounded below. So the degree d piece is 0 for d sufficiently negative. But it goes up forever, because it's like polynomials, the grading goes up forever. And let's see what, we just looked at the irreducible representations of the nil-Hecke algebra. The irreducible graded modules, well, there was only one of them up to isomorphism and degree shift, and it was actually finite dimensional. Its dimension was n factorial. Even though the nil-Hecke algebra itself is this infinite dimensional algebra, because it's graded finite dimensional and bounded below, it gives you the irreducible graded modules are not bad. So let's just write that out a little bit more generally. If you have any graded unital algebra A, like the nil-Hecke algebra, but any graded and unital. But last time I was actually interested more in this sort of locally unital setting where you didn't have a 1. But at least if you're unital, like the nil-Hecke algebra, and your graded pieces are finite dimensional, you're graded finite dimensional, and you're bounded below, then those properties about irreducible modules for the nil-Hecke algebra carry over to A. The number of graded irreducibles up to isomorphism and degree shift is finite. In the nil-Hecke algebra it was 1, but it's always finite. Your graded finite dimensional and bounded below. Any finitely generated graded module is itself graded finite dimensional and bounded below. Because, well, the regular module itself, that's why that is. Any finitely co-generated graded module, it kind of looks like the dual of a finitely generated one. Any finitely co-generated graded module is also graded finite dimensional, but now bounded above instead of bounded below. That's the difference. And irreducible graded modules, they're both finitely generated and finitely co-generated. So they're graded finite dimensional, their graded pieces are all finite, and they're bounded both below and above, so there are only finitely many degrees that show up in that graded irreducible. So graded irreducibles are actually globally finite dimensional. Their Q dimension would actually just be a formal Laurent series in Q rather than being a power series. Not formal Laurent, it's just a Laurent polynomial rather than being the formal Laurent series, which would be the general case. And so that property that this irreducible graded module, the nil-Hecke algebra was just finite dimensional, that's just a consequence of the nil-Hecke algebra being graded finite dimensional and bounded below. That's going to be important. And I've written down one more property about this sort of algebra A, which is maybe less familiar, but it's extremely important for what we're doing. If you have your unital graded algebra that's graded finite dimensional and bounded below, then any graded module V that is itself graded finite dimensional and bounded below. I love those properties. Any. There's absolutely no assumption of V about it being finitely generated or anything like that. All you need is that V is itself graded finite dimensional and bounded below. Then V has a projective cover in the category of graded A modules. That projective cover, it'll coincide with the projective cover of the head of V. But the head of V will, if it's not finitely generated, will be some infinite direct sum of irreducibles. It's kind of scary in this subject. I actually have to take projective covers of infinite direct, of modules that are not themselves finitely generated. But everything's fine. Providing V is graded finite dimensional bounded below, it has a projective cover, which is again graded finite dimensional and bounded below. It will just be a projective cover of the head, even though that's an infinite direct sum of irreducibles. That's kind of a little weird fact. It lets you remove finite generation pretty much everywhere. You replace it by this graded finite dimensional bounded below property instead. And then all your usual stuff like Nakayama lemma, where you have finite dimensionality, works instead of this setting. It lets you throw away Noetherian when you're doing kind of usual arguments. You really don't need Noetherian, just this graded finite dimensional bounded below replaces that. It's kind of nice. All right. So everything's graded. So of course now what I've got to do is I've got to take the definition from last time of triangular basis and just think through what happens when you have a grading instead. So of course this is called graded triangular basis, and there's absolutely nothing surprising. In fact, this slide is just the slide from yesterday. So I haven't done anything yet. Oh no, I did do one thing. For the example I'm going to do today, the natural partial order to use is the opposite of the convention for the partial order from last time. So I'm afraid I've flipped less than or equal to greater than or equal everywhere. Remember my post set was upper finite last time, and now I changed the word upper to the word lower. I'm just switching the partial order so we don't get confused later on. In fact, later on the post set is going to be the natural numbers, the natural ordering, and it would be really confusing if I didn't make that switch at this point. So everything here, for example, that inequality in the triangularity is the other way around from this slide yesterday. That's a trivial change. We need to incorporate grading. So let me go ahead and do that. So now what's changing is that the algebra is a graded algebra. My idempotents should be homogeneous idempotents. So the idempotents are in degree 0, that's false. And I don't want to insist, remember last time I insisted that it was locally finite dimensional. So each of these summands, 1A, remember I had these distinguished idempotents indexed by the set I, and all those pieces, 1I, A, 1J, had to be finite dimensional. That's what I meant by locally finite dimensional. Now we're in this graded setting, so they need to be locally graded finite dimensional and bounded below. So each of these 1I, A, 1Js has to be graded finite dimensional. Where do I put it on my space? It has to be graded finite dimensional. For each I and J, 1I, A, 1J has to be graded finite dimensional and bounded below. So that we're in this. But remember, I might have infinitely many of these idempotents. A now needn't be unital like it was earlier today. But each of these pieces, 1I, A, 1J, has some sort of reasonable finiteness about the grading. It's graded finite dimensional and bounded below. It's a very strange setup. And then everything else is the same. Yeah, all the same. I guess I want remember then we had this triangular basis, which were these products, X, H, Y, where X was like upper triangular, H was like diagonal, and Y was lower triangular, with respect to this partial order that we had around, and that was my triangular basis, and the triangularity axiom was that very easy thing to check, and then we were in business. I guess it's reasonable to insist that the x's, h's, and y's are homogeneous now that they're elements of a graded vector space. So let's just say I want this to be a homogeneous basis. It's no big deal. Whereas last time these sets of basis vectors in each weight were finite sets, these are now going to be infinite sets. But in each degree they're going to be finite, but there's infinitely many degrees shown. And below. Okay. Very stupid extension of the definition from last time, no big deal. But I've now really weakened the finiteness. Instead of this being a finite dimensional vector space, it's merely graded finite dimensional and bounded below. And this next slide is also from last time. Once you had a triangular basis, the point is it's a practical way of understanding something about modules over that algebra. And I'm going to do the same thing. I'm going to just adapt what we did last time. Instead of looking at A modules, of course, I'm now looking at graded A modules. Help me out if I missed writing a G somewhere. Where else do I need G's? Maybe down here. So these are locally unital graded modules. Right, so that means as well as being the direct sum of these pieces when you hit them with the distinguished idempotents, it's also Z graded. So you have these V sub D is the degree D piece. So it's kind of like a bi-grading, I guess, by the I's and these idempotents and by Z. I think everything else is the same. So I flipped the partial order around. You remember I went from A to these quotients, A greater than or equal to lambda. Last time that was A less than or equal to lambda, no big deal. And then once I had A greater than or equal to lambda, I then cut it with this weight idempotent to get this algebra A lambda, which last time was a finite dimensional algebra. Now it's merely a locally finite dimensional and bounded below unital algebra. These are algebras A lambda. They played the role of the Cartan subalgebra in when we were doing this sort of standardization process. So the Cartans in this graded theory, these A lambdas, they're unital graded algebras that are locally finite dimensional and bounded below. That was what the Nil-Hecke algebra is an example of such an A lambda. And in a minute I'm going to give you an example where indeed the Cartan part of my graded algebra consists of all the Nil-Hecke algebras for all A. Okay, so that's why I was discussing a little bit, what do I know about unital graded algebras that are locally finite dimensional and bounded below, because those algebras are going to show up as the Cartans of the algebra A that I'm really interested in. And then everything else goes through from last time. You have these this Recolmo situation that I talked a little bit about last time.
Will there be grading shifts in the functor now?
No. But the functors are defined in exactly the same way. They're naturally functors between grading modules. I don't put in any extra grading shifts. The adjunction between Hence and Hom is a degree 0 adjunction. So you don't need any grading shifts to fix that sort of thing. And then I'm still carrying on doing what I did my 6 out of 10 part yesterday. I've got this standardization functor, this J-Shriek functor, that I use to build standard modules, and I'm going to do exactly the same thing to build the standard module delta of B, the proper standard module delta bar of B, and the co-standards, those nablas, by standardizing and co-standardizing. These are all now going to be graded modules, because everything's graded, right? So you remember how it went? I needed to pick for each weight lambda, I needed to pick a set B lambda. It's still going to be a finite set because A lambda has finitely many irreducible graded modules. Now I'm doing everything up to isomorphism and grading shift. So these L lambda of B's, they're representatives now up to isomorphism and grading shift. So pick one for each. So B lambda indexes the irreducible A lambdas modules, and I pick such graded module. So I'm making a choice of the grading shift for each irreducible up to isomorphism we have around. And remember, P lambda of B and I lambda of B was the projective cover and the injective hull as a graded A lambda module. And then standardizing the graded projectives or standardizing the graded irreducibles give you these standard modules and these proper standard modules. And the theorem goes through from last time that if you take the heads of the standard modules, in the category of graded modules, of course, now these L of B's, they give a complete set of graded irreducible A modules, now indexed by this set big B, which is the disjoint union of all of those little local sets B lambdas, where I had this kind of B sitting over our post set. That was my setup. You get the classification of the irreducible graded modules L of B. I guess I need the word graded in there. Ooh, am I messing up? Okay, there we go. This. Yes, I need the graded modules. With a full set of graded irreducible A modules up to isomorphism and degree shift. And then the whole point of this setup is it's kind of, we've got this setup where you get BGG reciprocity for free out of this general setup. So P of B, if you remember, P of B was the projective cover of L of B. This has what I call a delta flag, so it has a filtration by these standard modules, and now it's the graded multiplicity of standard module delta of C in projective indecomposable module P of B that's the same as the graded composition multiplicity of L of B in the proper co-standard module nabla bar of C. And I think there's a Q inverse there because the grading gets switched around in this BGG reciprocity. However, the definition of delta flag to get BGG reciprocity is not as easy as it was yesterday. Yesterday, delta flag was just a finite filtration of your module where the sections were standard modules. The new thing that shows up now in this graded theory is you need to reinterpret what you mean by a delta flag in a graded module V. It's a finite filtration, V1, V2, V3 into V, whose sections, they're no longer, and this is no longer correct because that should be a standard module, but otherwise it was good. The sections are no longer single standard modules. You need to allow sections that are infinite direct sums of standard modules from the same stratum for the same lambda, infinite direct sums that are locally finite dimensional, that are graded finite dimensional and bounded below. So you get infinite direct sums to some formal Laurent series in Q inverse here. Although it's an infinite direct sum, in each layer it's still locally finite dimensional and bounded below. So this is somehow a scary thing. Suddenly you have to allow these sections in your delta flags that are genuine infinite direct sums. But in a way you can still kind of count. It's just you count no longer with natural numbers, you count with formal Laurent series in Q inverse, because that's this locally finite dimensional bounded below property. So it's really a weird new feature that kind of comes at you as soon as you introduce grading in this tool. Alright.
Sorry, I have a slight objection. So this BGG reciprocity, I mean, I would call it more Brouwer-Humphreys reciprocity.
Fair enough.
From a historical.
I'm never going to change, but you should call it that.
Okay, all right. Okay.
I can't make myself do it. But it's totally fair.
Yeah,
I should really call it Brouwer BGG Humphreys reciprocity.
Yeah.
But hey,
Actually, Humphreys work preceded BGG. So.
then absolutely.
Okay.
All right. So there's my general theory. And just like last time, I gave you the general theory and I gave you the classical example. Now I've got this graded modification of the general theory. Actually, the example came first, and is why we set up that graded modification. It's meant to be just a practical tool for this example. So this is kind of custom made for the example I'm going to show you now. So now this is going to be important, and I am going to use this tomorrow as well, this example. This is kind of really what I'm interested in. So the example is called the nil-Brouwer category. Last time my example was the Q-shirt category, and that was a monoidal category, and I gave you a presentation for it in terms of string calculus. I'm going to do exactly the same here with this nil-Brouwer category. It's going to be a strict, graded, k-linear monoidal category. Okay, so nil-Brouwer category. It depends on a parameter t. So I'm working over my field k. I'm going to fix that parameter t in the field, and I denote this category by NB. That's the fancy font I use for categories that I can't draw. Subscript t, which is the parameter. Okay, so that's the nil-Brouwer category for parameter t. It's for a very elegant, very simple presentation. I'm just going to write that down, just a diagrammatic presentation as a strict graded monoidal category. It's actually only got one generating object, which I call capital B. One generating object. This is a monoidal presentation, so that means a general object is a tensor product of n copies of B. B star, B star, B there. So a general object is B star n, indexed by a natural number n. And really the object set's just the natural numbers, but it's these B star n's. In my string diagrams, I denote the identity endomorphism of B, 1 sub B, just by a single string. Or if I had this object B star n, the identity endomorphism of B star n is just n parallel strings. And often I'll just denote that by 1 sub n, because it looks a bit silly to write 1 sub B star n. Okay, so one generating object B, and then there are 4 generating morphisms. You can see them down there at the bottom. One is denoted by a dot on the string, so that would be a morphism from B to B. I start writing at the bottom of the page, so that's how it goes. So this goes from B to B. The dot is in degree 2. Think of that as being like these polynomial generators x, which is in degree 2. The next generator is the crossing, which goes from B star B to B star B. The crossing is in degree -2. Think of that as being like this de Maizière operator tau in the Rouquier category earlier. And then there's a cap and a cup, which are both degree 0. They're just going to, so the cap goes from B star B to the unit object, the cup goes from the unit object to B star B. They're just going to make B into a self-dual object. So this sort of self-adjunction of degree 0 between B and self. Okay, relations. So here are the relations, and indeed, there's these. Let's see, my pencils run out of power. That's never good. So there's my zigzag relations. That's just saying that B is a self-dual object. That's what we're talking about. Other relations. Crossing squared is 0. That's like de Maizière tau squared is 0 in the Noetherian category. Honest braid relation for crossings. This relation is a little, I guess this one, this is this curl. The curl is 0. I mean, everything's as easy as that. It's a very simple presentation, but this sort of thing will look familiar to a bunch of you. You need to know how to pull a dot past a crossing. This is how x commutes with tau. If you just had, if you were writing this nil-Hecke algebra as we do in this categorification subject, if you were drawing this diagrammatically, the dot would go past the crossing and you get an error term which would be the identity. Not quite that. In the nil-Brouwer category, when dot goes past crossing, you get an identity minus this cup-cap pair. That's a little bit weird, but that's the most interesting relation. I guess this deserves a bit of attention. When you pull a dot over a cap or a cup, you get a sign change. But it's okay, you can kind of slide a crossing over a cup or a cap. These sort of pitchfork relations are fine with no sign. But dots, when dots go over critical points, the sign changes. And then the final relation is this bubble. That's the cup followed by the cap. That's what the parameter t is. The bubble is just t times the unit object. So this is a very simple bunch of relations. The relations should look kind of familiar to people who've seen this sort of stuff before.
So because this special relation, x is not really, the dot is not really corresponding to the x, right?
This is not the nil-Hecke algebra. This is the nil-Brouwer category. And this dot relation is not the nil-Hecke relation. It's a new relation. This is a new object, the nil-Brouwer category. Let me just do one thing, because it's easy and it's good. So if I take this relation that we were just talking about, my dot sliding relation, how x goes past tau, and I compose with a cup and a cap on top, you get that relation. Now, this is a curl. Curl is 0. This is an upside down curl. It's easy enough to see that that's 0 as well by doing some obvious little game. So the left hand side is just 0. That's a 0. Maybe I put a slash through it so you can see it's a 0. That's a bubble. Bubble is t times the unit object. And this is 2 bubbles. Each bubble is t. Okay, so therefore t squared minus t is 0. So if you want this category to not be trivial, for not to be simply totally 0, we're over a field, you better have that either t is 0 or t is 1 from there, right there. So I said t was a parameter, but actually there are only 2 choices. T is 0 or t is 1. And then you see how it's kind of a trivial little game. All right. So that's the nil-Brouwer category. I've been working with this for a little while, and it's a remarkably lovely category, and I'm kind of surprised that I have never seen it before, because it's kind of very natural. Well, it is what it is. Right, so let me tell you a little bit about the nil-Brouwer category. The first thing I'd like to tell you about is what the endomorphism algebra of the unit object is. This is kind of the first thing you should think about when you have some monoidal category in front of you. What is the endomorphism algebra of the unit object? That's these bubbles, right? This bubble that I had before, that's a morphism from empty to empty. That bubble is an endomorphism of the unit object. My relation said that bubble is just this scalar t, 0 or 1. But there's more endomorphisms of the unit object than just the bubble, because you can take a cup and then you can put some number of dots on it, and then it can. So you have all these dotted bubbles. They're all endomorphisms of the unit object as well. And no relation tells you about them. Okay, so I'm going to let gamma, this is kind of standard notation, gamma is this algebra of Q functions. So it's the subalgebra of the usual, we're working over a field K. It's a subalgebra of the usual algebra of symmetric functions. In there you've got elementary symmetric functions ER and complete symmetric functions HR. The little QRs, this is their definition. QR is the sum of the EH's, elementary times complete, where you can see the formula there. These Schur's little Q functions, and gamma is going to be the subalgebra of the algebra of symmetric functions generated by these Schur little Q functions. So here's the first theorem about the Nil-Brauer category. The endomorphism algebra of the unit object is isomorphic to this ring gamma of Schur Q functions. The little QR guy goes to this dotted bubble with R dots, some scalar at the front. I think I forgot to say that my field K is not allowed to have characteristic 2. Okay? Throw away characteristic 2. So you absolutely need to be able to invert 2 in many, many places in this story. It's not a big deal. And then that's a true statement. It's really annoying when you define a monoidal category by generating relations, because, well, it's annoying when you define anything by generating relations. So, even though it's kind of quick, you have to do some work to convince yourself. I mean, for it to even be not 0, we found that there was some constraints on our parameter t. So this theorem gives you a basis for all morphism spaces. N1 is a particular morphism space, right, from 0 to 0. It's got a basis given by these dotted bubbles, or monomials in them, just like this ring gamma of Schur Q functions has its basis. But in general, to get a basis for Hom NM in the Nil-Brauer category, you see, maybe I can just draw a picture here. Do this. Yeah, so you've got what am I doing? Hom NM. So you've got n strings at the bottom. You've got m strings at the top, and you've got these cups, caps, and crossings. Now I can try and do some sort of picture like that. There's a sort of typical picture that you can get. I mean, it can get very complicated, right? So what you've got to do is you've got to, for each, but so far I haven't put any dots on. So it's just like a combinatorial picture, like drawing a permutation, except I've got some cups and caps. It's some sort of combinatorial matching between the vertices. And the relations let you do things like that you could move this crossing around. Maybe if I had another vertex so that it was a little bit more interesting, you could kind of do something like that. And you can of course, you've got braid relations around. The basis theorem says, okay, for each possible matching, pick your favorite reduced matching.
Is QR like PR or something?
QR is QR. That's what it is. It's like QR. There it is. I can't. This is the notation McDonald uses. So
I swear I've seen a symmetric function identity where the right-hand side is a well-known symmetric function.
well, in McDonald it's called little QR. Is what it is. Okay. Then there's these Schur big Q functions labeled by strict partitions and these Schur big P functions as well. They're all part of this story, but these are the simplest things. I mean, everyone should see them a lot because it's elementary times complete symmetric functions. Okay, so basis, right? So for each matching, you pick your favorite reduced matching. When I say reduced, I mean you're not allowed to have any self-intersections of a string. Remember, curls are 0. So you can always get rid of self-intersections. Two different strings are not allowed to cross each other twice. Remember, the crossing squared is 0 in here. So it's not quite like taking, I don't know, doing the braid group or something like that, but it's very similar. It's just the same sort of notion of reduced. And then you have to pick some distinguished point on each string. You can pick it wherever you like. And put some number of dots at that distinguished point in each string. This is the obvious thing that could be a basis, and the theorem says this is a basis for this morphism space as a free gamma module. Gamma end of 1, of course, you can put any number of dotted bubbles on the edge there that are in gamma. So as a free gamma module, those obvious kind of reduced dotted diagrams are a basis. Actually, I mean, once you've got so this basis, there's some choice. I'm now going to make that choice a little bit carefully so that this basis is a graded triangular basis, because that's what the talk is all about, right? So the third part says that okay, like I did last time, I've got this k-linear category. I like to put all the Hom spaces together as a direct sum to take the path algebra, and that's then a graded locally unital algebra, which I'm just going to use Roman NB. The T is fixed. I'm going to write NB for the path algebra of the Nil-Brouwer category. So down there at the bottom, that's the path algebra. This algebra has a graded triangular basis. It's meant to be an example of that, right? So the path algebra of the Nil-Brouwer category has such a basis. The set I indexing my special idempotence, that's the object set of this category, it's just natural numbers. Special idempotence, same set. Weight post set lambda, same set, natural numbers. Partial order, natural order, or natural numbers. It's kind of a very simple example. I need to tell you what the triangular basis is. Remember, that's this XHY. You need to know what the basis XHY is. And this is such a great example because it's just straight in front of you. This is just naturally triangular, this category. So here I've drawn a typical one of these kind of reduced matchings with cups, caps, and crossings. And you can see on each string I've picked a distinguished point to put my dots. And on the right-hand edge I've got some of these dotted bubbles. That's just the notation I use for these dotted bubbles, those O's on the right there. So those are our little Schur Q functions there. And I pick my distinguished matchings in my basis so that all the cups are at the top, all the crossings are in the middle, and all the caps are at the bottom. Other than there's some bubbles, I put the bubbles in the middle as well. That is the triangular picture. The X part of the basis, they're the diagrams where there are only cups, no propagating strings cross. The H part of the basis is now highly non-trivial. That's where all the crossings of propagating strings occur. There can be some dots and some bubbles. And then the Y part of the basis, that's where there's just caps. By the basis theory, this is a basis. The axioms of graded triangular basis are trivial to check. This is such a thing. So I'm going to just finish up in like 3 minutes and tell you some consequences. It's such an easy example. Once you prove this basis theorem, which is not easy, it's totally visible that this basis has this triangular structure: cups, crossings, caps. What do you do? Well, then you work out what's your cartan. Our post set is natural numbers. So what's the cartan part, NB sub n? Remember how that goes? You have to take the whole path algebra. You set idempotence m less than n to 0. That gives you this quotient algebra NB greater than or equal to n. And then you do the idempotent cup 1n. Well, NBN, it's just the usual Nil-Hecke algebra on n strings. The nth part of the cartan is just the Nil-Hecke algebra on n strings. nil hecka n. So this is NBN, right? It's nothing. Oh, it's just not over the ground field K. It's over this ring gamma instead, right? So it's just tensored up from K to gamma. And you can see this very, very easily. I mean, we had this relation, for example, in the Nil-Brouwer category. When you go to this subquotient, this morphism here is sort of factoring through a smaller object. So it exactly gets killed off when you pass to this subquotient, it's the cartan, and you get the usual relation for the x and the tau in the nil-hecka category. It's that easy, but you see how this cartan is no way a subalgebra. It's got to be a subquotient in this setup. And so the cartan part of the Nil-Brouwer category is the nil-hecka algebras for all n. And then you're in business, right? You can then take the you can take the indecomposable projectives for your cartan part. It's actually not the Pn. It's not quite. It's polynomials, but not over the field K, but over gamma. That's what you have to use there because we've got all these bubbles, and you get the standard module by standardizing. You get the proper standard module by standardizing the irreducible module for the nth nil-hecka algebra. Remember that guy of dimension n factorial. The standard module has irreducible head L of n, projective cover P of n. The theorem tells you these L of n's for all natural numbers n give you all the irreducible graded representations of the Nil-Brouwer category. The projectives have BGG reciprocity and so on, and you're in business. I made a point of saying how these delta flags were infinite direct sums in this story, which is the sort of new feature of this graded world that makes it actually unlike pretty much anything I've seen in Lie theory before. It's kind of a weird new phenomenon that in delta flags you need possibly infinite direct sums of standard modules in each layer, but still low graded finite dimensional and bounded below. And that is indeed the case here. The indecomposable projective, the nth P of n, the projective cover of L of n, the natural number n, by the structure theory of these graded triangular bases, it has a delta flag. The top section of the delta flag is delta of n, the standard module, and then the next layer down you get delta n minus 2 and then delta n minus 4 and so on, but appearing with a direct sum that's some formal Laurent series in Q inverse that's genuinely infinite. So these are cyclic modules, these indecomposable projectives, but they have submodules that are infinite direct sums. You exactly see that this is not Noetherian, this world. Here's a submodule of a cyclic module that's not finitely generated. So it's really weird that you can manage this. And it goes back to that little lemma I mentioned about projective covers for these unital graded algebras at the beginning that still have a good theory of projective covers. That's what's appearing in these sections. I've just got a couple of theorems to just put up. Actually, this is a truly miraculous situation. I can exactly tell you what the graded multiplicity of the standard module delta n in the indecomposable projective is. By BGG reciprocity, it's the same as the graded composition multiplicity of L of n plus 2m in the proper standard module delta bar m. And so these delta flags of projectives, there's finitely many layers, because there's only finitely many natural numbers below n. This is kind of lowest weight theory, because I flipped the partial order. But in the proper standard modules, their composition factors get bigger. Inside the nth proper standard, you get irreducibles Ln plus 2m, and with the posets's the natural number, so you can go up for, there's infinitely many different composition factors here. And these graded multiplicities, well, I've written them as rational functions, because you've got to expand that as a formal Laurent series in Q inverse. And you of course see it's a very big infinite thing, right? This is a really scary, it's in no way a Laurent polynomial here. But it's kind of remarkable, it just depends on the parity of n and t here, which two cases. And even though these are crazy infinite series, the Nil-Brouwer category is such a beautiful example that you can completely compute. Maybe one more theorem, just a very similar flavor. These irreducibles for the Nil-Brouwer category L of n's, these graded irreducibles.
Sorry, in the earlier slide, is in the reciprocity, isn't there some standard costandard flip?
There is. I cheated you here. I should have nabla bar and I should have a Q inverse down there. But actually, the nil-Brouwer category has a duality which flips diagrams, and in the presence of duality, you can do what I've done here. Then it looks nicer.
Are you taking like B equals nabla? I'm sorry, B equals like capital lambda?
Yes, so the set B, yeah, again, the set, everything is the natural numbers.
Okay.
All in the general setup, yes, I had all these complicated sets, but in this case, they're all just natural numbers. So the index set for these irreducibles is the natural numbers, that's L of n. Just very last theorem. So we've got these irreducible graded modules L of n. These are the irreducible representations of the Nil-Brouwer category, or its path algebra, if you like to use just ordinary modules. And so what I've got here is I've got the graded character of L of n, and that means the obvious thing, right? So you take L of n, it's got all these different weight spaces, 1 sub m L of n. That's the m weight space of L of n. That's a graded vector space. Take its graded dimension. This will actually be just a Laurent polynomial in this case for irreducibles. You don't get these power series showing up. And then I have this formal variables. I use xi, which is just a sort of placeholder in this generating function that's my graded character. So this is the graded character of the irreducible, and there's a very simple clean formula for that graded character. It's a Laurent polynomial in Q, that's the grading, and then its formal power series in this generating, it's just a generating function in this formal variable xi. So you take this guy, look, this is on the denominator, is 1 minus quantum k squared, xi squared. You have to just expand that as a formal series in xi, and then read off the coefficients of xi to the m, and it gives you exactly graded characters of the weight spaces of these irreducibles. Okay, so these theorems are totally remarkable. This is not something you expect, but the infiniteness is what I find remarkable. That these theorems, the kind of things we're used to in Lie theory, that I've never seen them before, where you get these infinite direct sums, but in a manageable way. And next time, I'll explain why, and I'll tell you what the Nil-Brouwer category categorifies, and then hopefully it all makes sense.
Sorry. So in the triangular basis decomposition of the algebras, so in the two examples that you've done so far, all the algebras came from some like type of you take like a category, and then you like look at these pieces and put them together.
Yeah, I mean that's really what I like to do, right? I really like these strict monoidal categories.
Is there some way you can take this triangular basis and lift it to like the categorical level, so you have these like subcategories of your original category that behave like, ups and downs and middle parts?
So Sam and Snowden have tried doing something like this. They have what they call a triangular monoidal category, where they do that, and it's quite nice and it's better. But here, my notion of triangular basis is a very, very mild, weak thing. The x's, for example, don't span a subalgebra of my algebra. The h's don't give you a subalgebra of the algebra. You have to go to the subquotient. And so the triangular basis is actually a very, very weak condition. It's just a tool to set this theory up.
So this, even though this is on the algebra level, this is like
So I have basically forgotten the monoidal structure in setting this up. But remember, there's a way to remember the monoidal structure back again, because it induces an induction product on your module category. So you have this induction product, and then it becomes natural to think, well, okay, maybe in general this induction product is not bi-exact. For the example yesterday it is, but in general when you play this game with induction product coming from a monoidal category here, that's the structure that the monoidal product gives you. You get a tensor product on your abelian category, but it's not a bi-exact tensor product. Then you start thinking, well, okay, but maybe it is when I restrict to modules with delta flags, and that seems to be the case. And, yeah.
So their triangular category and this triangular basis for algebra story, they're not like the same.
So Sam and Snowden have a much more restrictive thing they call triangular category, and it's really nice when you have that. An example is the usual Brouwer category. It is a triangular monoidal category, And they have nice tools then, they typically use that to prove that indeed their examples are Noetherian by using by passing down to the Borel subcategory. These are not Noetherian. We're in this very different, weird kind of new world where it's a bit surprising to me that we can cope, but we can.